Far beyond the quiet glow of ordinary galaxies, there is one cosmic giant that seems almost impossible. UGC 1259, one spins so fast, so massively, that it feels as if gravity itself should lose its grip. And yet, it remains intact, holding one of the deepest mysteries in the known universe. Tonight, this journey moves into the silent darkness around a galaxy that challenges everything instinct suggests about mass, motion, and cosmic balance. If this kind of deep space mystery is worth exploring, please like the video, subscribe to the channel, and settle in for the story of the mystery of UGC 1259, a galaxy that defies gravity, far beyond the visible outline of any one galaxy. The universe arranges matter on scales so large that ordinary landscapes no longer offer a useful comparison. It does not spread galaxies evenly in all directions. It gathers them into long filaments, broad sheets, crowded knots, and wide regions with far fewer galaxies than average. This immense pattern is known as the cosmic web. A web in this sense is a connected structure, shaped over long ages by gravity acting on matter that begins with tiny differences in density. Where matter starts slightly denser than its surroundings, gravity slowly strengthens that difference. Gas and dark matter drift inward. Galaxies form and continue to collect along the same lines. Over billions of years, the result is a universe that appears laced together by structures of extraordinary size. Within this larger arrangement, UGC 12591 belongs not to an empty and solitary void, but to a richly populated corridor of the nearby universe. It is associated with the Pisces-Perseus supercluster, one of the most striking elongated concentrations of galaxies in the local cosmic web. A supercluster is not a single compact object like a star cluster. It is a much broader association of galaxy groups, clusters, and filaments that stretch across immense distances. In such a setting, gravity does not pull everything into one neat sphere. Instead, matter follows the shape of the original large-scale flows, leaving behind a long uneven spine of structure. The Pisces-Perseus system is one of these spines, a giant chain in which galaxies and clusters appear linked across the sky by shared large-scale geography. At this scale, individual galaxies are almost impossible to imagine as separate worlds with their own internal detail. They become points of light embedded in a pattern that is larger than any one of them can control. UGC 12591 enters the story in this outermost setting as one member of that larger architecture. Its unusual speed, mass, and structure remain hidden at this distance. Here, only the environment matters. The galaxy is first a location in a map of matter, a place where the broad flows of the universe have deposited one more luminous system inside a long-developed framework. This framework begins very early in cosmic history. After the hot early phase of the universe cools enough for matter and radiation to separate, slight variations in density remain. They are tiny, but gravity is patient. Dark matter, which does not shine or absorb light in the ordinary way, provides much of the underlying gravitational scaffold. Ordinary matter then falls into the same broad wells. Gas collects, cools, and forms stars. Galaxies arise where enough matter gathers and remains bound. Over time, the largest features grow first in outline and then in complexity. Filaments feed clusters, groups merge. Some galaxies fall inward toward dense centers. Others remain along the long connective lanes between those centers. The outer setting of UGC 12591 is therefore not accidental. It is the result of a deep history of accumulation on scales far larger than the galaxy itself. The cosmic web also shapes motion, though this motion is not visible in a simple glance at the sky. Galaxies do not merely sit in place like fixed lamps. They move under the combined pull of nearby neighbours and distant concentrations of mass. In a supercluster region, these motions can become intricate. Some galaxies drift toward groups or clusters. Some orbit within local associations. Some continue along filaments with speeds that reflect the surrounding distribution of matter. The measured recession of a galaxy, seen through the stretching of light by cosmic expansion, contains both the general expansion of the universe and these smaller local motions. In a setting like Pisces Perseus, this means that environment must always be considered before any one galaxy is treated as fully isolated in a physical sense. Even so, the large-scale setting remains calmer than the crowded interior of a rich cluster. In the outer cosmic web, space is still vast. The average separation between galaxies is immense by ordinary standards. Collisions are not constant events. Most of the volume is dark, cold, and nearly empty, with matter concentrated into narrow lanes and denser nodes. Between these concentrations lie voids, enormous regions where galaxies are relatively scarce. The contrast gives the web its shape. It is a structure defined as much by absence as by presence. UGC 12591 occupies a place in the populated side of this contrast. It belongs to a region where matter has gathered enough to create a visible chain, yet the surrounding volume remains dominated by darkness and distance. Light itself reinforces this sense of scale. The light that carries knowledge of such a galaxy crosses millions of years before reaching telescopes. During that journey, it passes through a universe that is mostly transparent, expanding, and thinly filled with gas. The galaxy remains embedded in its supercluster environment the entire time, but the observer receives that information as a flattened projection on the sky. Large-scale maps are needed to recover the true three-dimensional arrangement. Surveys of galaxy positions and velocities reveal that the visible points are not scattered randomly. They trace the same filamentary geometry predicted by modern cosmology and seen in numerical simulations. UGC 12591 appears, in this way, as both an observed galaxy and a marker of deeper structure. This outer view also keeps expectation under control. A galaxy with extraordinary internal properties may still arise in a universe governed by ordinary laws. The cosmic web does not require exceptions to gravity. It is one of gravity's grandest outcomes. Its filaments and nodes show what happens when matter responds to attraction over immense spans of time. In that sense, the setting of UGC 12591 is not exotic. It is a natural part of the large-scale universe. What makes it notable lies not in the existence of the web around it, but in how one particular galaxy comes to inhabit that web with such remarkable internal motion. At this outermost stage, however, none of those details yet enter the frame. Only the broadest truths remain visible here. The universe is structured rather than smooth. Dark matter and ordinary matter gather into connected forms. Superclusters mark some of the largest concentrations in the nearby cosmos. The Pisces Perseus chain stands as one of the clearest examples of such order on a grand scale. UGC 12591 rests within that great arrangement as a distant luminous member, carried by the same long history of gravitational assembly that shapes the web itself. In the far exterior view, the galaxy is not yet a rotating disk, not yet a record holder, not yet a problem of mass and motion. It is first a point in the vast architecture of matter, suspended within one strand of the living cosmic web. Within the large structure of the Pisces-Perseus region, the galaxy now comes into clearer view as a single observed object with a measurable place in the sky and a measurable distance in space. At this level, the broad web of matter gives way to astronomy in its practical form. A telescope does not first encounter a galaxy as a theory. It encounters light. That light arrives with direction, brightness, colour, and spectral pattern. From those features, astronomers determine where the galaxy appears on the celestial sphere and how far away it is likely to be. UGC 1, 2, 5, 9. 1 emerges from the general background in this way, as a specific system recorded in catalogues, identified in imaging, and placed at a substantial distance from the Milky Way. Its distance is large enough that the galaxy is seen not as a nearby neighbour with easily resolved individual stars, but as a complete external system. The light that reaches Earth leaves the galaxy millions of years ago and travels across intergalactic space before entering the atmosphere and the instruments that record it. This travel time gives distance a second meaning. It is not only a separation in space, it is also a modest look into the past. The galaxy is observed not exactly as it is now, but as it appears when the departing light begins its journey. In the nearby universe this time, difference is not extreme compared with deep cosmological surveys, yet it is large enough to remind every observer that astronomy works through delayed arrival. All knowledge of distance in such cases begins with that patient crossing of light. The location of UGC 12591 on the sky places it in a region long studied for its concentration of galaxies. It lies in the direction of the northern constellations associated with the Pisces-Perseus chain, where surveys reveal many galaxies sharing similar recession speeds. This common pattern in redshift helps astronomers identify large-scale association. Redshift is the shift of spectral lines toward longer wavelengths. In the expanding universe, it usually indicates that a distant galaxy is receding as space itself stretches. For galaxies in the local and moderately distant universe, redshift serves as a practical first guide to distance. It does not tell the whole story on its own, because local gravitational motions can add to or subtract from the expansion signal, but it gives a strong framework within which the galaxy can be placed. UGC 12591 has a recession velocity that marks it as a distant member of the nearby extragalactic realm, rather than of the local group or its immediate surroundings. This means that its apparent size on the sky is much smaller than its true physical size. A galaxy that spans tens of thousands of light-years can still appear as a compact patch in a telescope image when placed far enough away. Converting that apparent width into a real diameter requires distance. Once the distance is estimated from redshift and related methods, the observed angular size can be turned into a physical scale. This step is simple in concept and profound in result. It converts a luminous blur into a system of known extent. It allows astronomers to speak not only of how large the galaxy looks, but of how large it actually is. Distance also gives meaning to luminosity, the true power of the galaxy's light output. A distant object appears dimmer than an equally luminous nearby one, because its light spreads out over a larger sphere before reaching the observer. For that reason, an apparently modest patch of light may in reality contain an immense number of stars. UGC 12591 proves to be one of these cases. Once placed at its measured distance, it is understood as a very large and very massive galaxy, rather than as a small faint system. This does not yet reveal the full reason for its importance, but it establishes the scale on which the later measurements must be interpreted. a very fast-rotating galaxy that is also physically large, belongs to a different class of object from a small compact system with the same apparent brightness. At this stage of the inward approach, one of the most important scientific tasks is caution. Distance estimates in the nearby and intermediate universe are rarely based on one number alone. They depend on an assumed cosmic expansion rate, corrections for motions relative to local large-scale structures, and the calibration of reference frames. Different studies may therefore quote slightly different distances for the same galaxy. These differences do not erase the main result. Observations consistently place UGC 12591 far beyond the Milky Way and far beyond the most immediate neighboring groups, at a distance large enough for its light to represent a mature external galaxy seen as a whole. The exact number may vary somewhat with method and adopted cosmological parameters, but the physical interpretation remains stable. The sky position of the galaxy also matters because observation depends on line of sight. A galaxy seen through a crowded foreground of stars and dust in the plane of the Milky Way can be difficult to measure cleanly. UGC 12591 is observed through a line of sight that allows its external form to be studied with useful clarity. Foreground stars from the Milky Way may still appear in the same field, but the galaxy itself remains distinct enough for its major structure, brightness profile, and spectral features to be analyzed. This practical advantage helps explain why it becomes such a notable object in rotational studies. Some galaxies may be unusual, yet poorly placed for observation. This one is both unusual and observable. Its catalogue name also reflects the path by which astronomy often approaches such systems. UGC stands for Uppsala General Catalogue, a major listing of galaxies in the northern sky. The number 12591 is not a physical descriptor. It is an entry in an ordered survey tradition, a marker that tells the observer that the galaxy has passed through the systematic work of classification and record-keeping. Behind such a simple label lies the quiet labour of imaging plates, measuring positions, estimating apparent diameters, and comparing one object with many others. Before a galaxy becomes famous for its motion, it is first a catalogue object among thousands. The transition from anonymous entry to scientifically exceptional case begins only when observations reveal properties that separate it from the rest. This level of description therefore holds the galaxy at a measured distance and in a defined place, but still outside its internal details. It is not yet necessary to speak of disk speed, dark matter, or the central bulge. The focus remains on orientation in the universe and on the practical meaning of a redshift, apparent size, and luminosity. UGC 12591 stands in the sky as a distant, bright, massive external galaxy located in the direction of one of the nearby universe's great structural chains. It is far enough away that its light arrives as the integrated glow of a complete stellar system, and close enough that careful observation can still recover its shape and motion. In this region of the story, the galaxy becomes fixed in place. It is no longer only a point in the cosmic web. It is a specific destination in the observed sky, with distance, scale, and presence, with its place in the sky and its broad distance established. The galaxy can now be considered in relation to the systems around it. This is the level at which environment becomes local rather than cosmic. The great filament of the supercluster still exists in the background, but it no longer dominates the description. Attention settles on nearby companions, possible interactions, and the degree to which UGC 12591 lives under the immediate influence of other galaxies. In this more local sense, observations present it as a relatively isolated system. That description does not mean complete solitude. In astronomy, isolation is usually a matter of degree. It means that no nearby companion of comparable size appears close enough to dominate the galaxy's present structure through strong tidal disturbance. A tidal effect is the distortion caused when gravity from one body pulls more strongly on one side of another body than on the other side. In galaxies, such effects can stretch disks, twist gas, trigger bursts of star formation, and rearrange motion on large scales. When two large galaxies pass near each other, their shapes often show the event. Tails of stars may extend outward, dust lanes can become irregular, gas may be funneled inward, outer disks can warp or become lopsided. In the case of UGC 12591, observations do not show the kind of severe present-day disruption expected from a recent close encounter with a similarly massive neighbour. This absence is important. It allows astronomers to interpret its rapid rotation as a long-standing property of the galaxy, rather than as a temporary confusion produced by an ongoing collision. The meaning of the local environment depends on both distance and mass. A small nearby dwarf galaxy may not disturb a giant disk very much. A large companion, even at a somewhat greater separation, may have more influence. For this reason, studies of galactic neighbourhood do not simply count visible objects. They ask how luminous those objects are, how far away they appear in projection, and whether their measured velocities suggest a genuine three-dimensional association. Projection alone can be misleading. Two galaxies may appear close together on the sky, while lying at very different distances along the line of sight. Only when position and velocity are considered together does the local setting become clearer. For UGC 12591, this fuller view supports the picture of a massive galaxy without an obvious close rival shaping its present form. This relative isolation matters because galaxies often carry the memory of their surroundings in subtle ways. A dense cluster environment can strip gas from a galaxy as it moves through hot intracluster medium. A group environment can lead to repeated minor encounters and gradual reshaping. A very close pair can exchange material directly. In contrast, a more isolated galaxy can preserve ordered motion over longer times if no major disturbance interrupts it. The disk of UGC 12591 appears consistent with this calmer local history. Its structure does not resemble a wreckage field. It resembles a system that has retained large-scale rotational order, even while carrying the signs of long internal evolution. Isolation does not imply a complete lack of past interaction. Few large galaxies pass through cosmic time without any accretion at all. Minor mergers, in which a large galaxy absorbs much smaller companions, are thought to be common. Gas can also fall in from the surrounding medium over long periods. These quieter forms of growth may leave traces in stellar populations, outer gas distribution, or fainter symmetries. Observations indicate that UGC 12591 may have experienced such ordinary evolutionary processes as most massive galaxies do, but they do not point to a dramatic recent event that fully explains its exceptional speed. This distinction is important. It keeps the galaxy within the framework of gradual cosmic assembly, while preserving the need to understand its unusually high mass and rotation on their own terms. The surrounding region also appears sparse enough to support another practical conclusion. The measured rotation of the galaxy is less likely to be contaminated by confusion with a very close interacting companion. When radio observations map neutral hydrogen, and optical observations trace emission from gas in the disk, nearby overlapping systems can complicate interpretation. Separate velocity components may blend together. Disturbed gas streams can masquerade as rotation. A relatively clean local setting reduces these risks. It does not remove all uncertainty, but it strengthens confidence that the observed high rotational speed belongs chiefly to UGC 12591 itself. There is also a deeper physical meaning in this moderate isolation. Galaxies that grow in less crowded local settings may continue to acquire gas without having it stripped away too efficiently by dense surroundings. At the same time, they may avoid the repeated strong encounters that can transform rotating disks into more chaotic stellar systems. This offers one possible context for how a massive fast disk can persist. Observations indicate that UGC 12591 retains a substantial disk despite its very large mass, and that fact already sets it apart from many other giant galaxies, which often become dominated by spheroidal structure and less orderly motion after rich histories of mergers. The local environment does not force that outcome here. Even the word isolated must still be used carefully. The galaxy is not outside gravity's network. It remains part of the supercluster chain and participates in the broader matter distribution of its region. More distant structures still contribute to the gravitational field in a cumulative sense. The point is narrower. On the scale of immediate galactic neighbours, no strong present interaction appears necessary to account for the observed shape and kinematics. This makes UGC 12591 especially valuable to astronomers. It can be studied as an extreme disk galaxy without the same level of confusion introduced by a major ongoing encounter. Its properties can therefore be compared more directly with models of mass distribution and rotational support. The local calm around the galaxy also changes the emotional scale of the scene. The cosmic web of the first view feels immense and crowded in a statistical sense. Yet here the galaxy occupies a broad dark volume with generous spacing between luminous systems. Even inside a supercluster corridor, a single galaxy can have room around it. Light from neighbours may still punctuate the region, but empty intergalactic space dominates the actual volume. UGC 12591 sits in that darkness as a large rotating system with no immediate giant companion pressing against its structure. It carries itself through the local universe with unusual speed, but without the visible turmoil that a close gravitational struggle would be expected to leave behind. At this stage, the galaxy is no longer only a distant point and not yet an object broken into its inner anatomy. It is a massive system in a relatively quiet neighbourhood, shaped more by its own retained mass and long-term history than by any obvious present assault from nearby equals. The supercluster remains the outer frame, but the immediate scene has thinned. The background crowd has fallen away. What remains is a single great galaxy standing with notable independence in its local surroundings, prepared to be examined next by its visible form rather than by the company it keeps. With the local neighbourhood described as relatively quiet, the galaxy can now be approached through its overall form. The first clear impression comes from its shape on the sky, its distribution of light, and the way its structure compares with familiar galaxy classes. UGC 12591 is often described as a large disk system with a prominent central bulge, and it has been classified in ways that place it between the clean categories of spiral and lenticular. A spiral galaxy is typically defined by a flattened rotating disk containing dust and gas, with spiral arms that trace patterns of star formation. A lenticular galaxy, also called an S0 galaxy, usually has a disk and bulge but shows less obvious spiral arm structure and often contains less interstellar gas. In practice, Many galaxies occupy an intermediate space, and their classification depends on image depth, wavelength, and how strongly features such as dust lanes and arm segments stand out. In optical images, UGC 12591 presents a broad flattened body, indicating a disk seen at a significant inclination rather than face-on. Inclination matters because it changes what can be measured and how confidently. A disk that is nearly edge-on shows dust lanes clearly as dark bands, where starlight is blocked by interstellar grains. It also allows line-of-sight velocity from rotating gas to be measured with strong projection, which helps in determining rotation speed. At the same time, an edge-on view can hide subtle spiral structure because arms overlap along the line of sight. A disk that is more moderately inclined may show arm patterns better, but reduces the apparent velocity component along the line of sight. UGC 12591 is observed at an angle that reveals both a disk silhouette and internal dust structure, while still allowing a strong measurement of rotation. The galaxy's bulge is visually significant. A bulge is a central concentration of stars that rises above the plane of the disk and contributes a large fraction of the light in the inner region. In many disk galaxies, the bulge can be small, leaving the disk as the dominant feature. In others, especially among lenticulars and early-type spirals, the bulge is large and rounder, giving the galaxy a more compact bright center. UGC 12591 belongs to the latter family. Its bright central region indicates a deep gravitational potential and a large stellar mass concentration in the inner parts. At this point in the outward-to-inward path, that bulge is described only as a visible structure, not yet as a dynamical engine. It sets the overall appearance and hints at a history of star formation and eternal evolution that has built a substantial central body. The disk extends far beyond the bulge, forming the main flattened component in such galaxies. The disk is the region where stars orbit in an ordered manner, where gas tends to settle into a thin layer, and where dust accumulates along the same plane. The outer disk typically shows a gradual decline in surface brightness, meaning that the light becomes fainter with distance from the center. Deep imaging often reveals that disks can extend farther than their brightest inner regions suggest, with faint starlight and gas continuing outward into the galaxy's outer gravitational domain. UGC 12591 is known to be very large, and its disk contributes to that impression. The full extent is best understood only after distance is applied, but even in images it appears as a substantial structure rather than a compact one. The question of spiral structure remains subtle. Some observations suggest that the galaxy shows limited or weak spiral arm features, while others emphasize its lenticular character. This is not unusual for a massive, bulge-dominated disk galaxy. Spiral patterns depend on the presence of cold gas, on disk stability, and on how density waves or other instabilities develop. A very massive disk with a large bulge can suppress strong spiral arms by stabilizing the inner disk against certain disturbances. Dust lanes and faint arm segments may still exist, but they may be less prominent than in a classic grand design spiral. The galaxy's classification as an early-type disk, near the boundary between spiral and lenticular, reflects this balance. It is a disk system, but not one dominated by bright open arms. Dust provides some of the most direct visible evidence that the disk contains interstellar material. Dust is made of tiny solid grains, mostly silicates and carbon-rich compounds, mixed into the gas between stars. It absorbs and scatters short-wavelength light more strongly than long-wavelength light, so it can produce dark lanes and reddish color gradients. In an inclined disk, dust lanes often appear along the midplane, where gas density is highest. UGC 1259 1 shows dust features consistent with an organized disk, indicating that it retains at least some cold interstellar medium. This matters because gas and dust are tied to star formation and to the tracers used to measure rotation. The overall shape also suggests a thickened component beyond the thin gas layer. In many massive disk galaxies, the stellar disk is not perfectly thin. Stars can occupy a thicker distribution, especially older stars that have had more time to be dynamically heated, meaning their orbits gain more vertical motion over time. A thick disk can be difficult to separate from a bulge in an edge-on system, but the combined light profile can hint at how much stellar mass lies above the plane. UGC 12591 appears to have a substantial vertical structure in its luminous body, consistent with a massive mature disk galaxy that has experienced long-term internal mixing and perhaps past minor accretion. At this level, the galaxy's form is not treated as an oddity, but as a coherent whole. It is not a chaotic, irregular galaxy. It is not an elliptical galaxy lacking a disk. It is a massive disk system with a large bulge and a disk that shows dust and ordered structure. Its classification in the early type disk family is consistent with many other large galaxies, yet its specific combination of size and internal motion will later separate it from typical cases. Here, the emphasis remains on what the eye and the image reveal. The galaxy looks like a system built for rotation, with a flattened disk that signals the importance of angular momentum and a central bulge that signals deep central mass. The physical reasons behind this form lie in the way galaxies assemble and settle. A disk forms when gas falls into a gravitational potential and retains enough angular momentum to flatten into a rotating plane. Stars then form within that disk and largely keep the disk's ordered motion. A bulge can form through several pathways, including early rapid star formation, the inward flow of gas, and the gradual rearrangement of stars through bars or other instabilities. Mergers can also build bulges, especially if they are substantial. But the presence of a strong disk suggests that any such events do not fully destroy the galaxy's rotationally supported structure. UGC 12591 therefore presents itself as a product of both order and concentration, a system where the disk survives and the center grows large. This completes the view of the galaxy's overall form. It stands as a large inclined disk with a prominent bulge, a hybrid appearance between lenticular and spiral, and visible signs of dust and organized structure. The exterior setting has narrowed to a clear outline. The galaxy now has a body with shape and category, ready to be examined next through the starlight and color that describe its materials and ages across that body. The galaxy's visible body becomes more informative when its light is separated by color and by wavelength. A galaxy does not shine in only one uniform tone. Its starlight carries a record of many stellar populations, each with different ages, temperatures, and compositions, while its dust changes that light by absorbing and scattering part of it before it escapes into space. In UGC 12591, this combined pattern of starlight and dust reveals a system whose appearance is shaped by maturity, by a strong central stellar concentration, and by a disk that still contains interstellar material, even though it forms stars at a low rate. The image therefore becomes more than a portrait. It becomes a map of the galaxy's visible matter. Blue light in a galaxy usually points toward hotter and younger stars. Redder light often indicates older stellar populations, though dust can also redden the light by blocking the shorter wavelengths more strongly. For that reason, color must be interpreted with care. A red region is not automatically old, and a blue region is not automatically young. Astronomers compare many wavelengths together, often from ultraviolet through visible and into infrared, to separate these effects. In UGC 12591, observations across this broad range support the picture of a massive galaxy whose main stellar body is dominated by older stars, especially in and around the bulge, while the disk contains dust and a more limited contribution from younger stars. The overall impression is not one of intense ongoing star formation. It is one of restrained activity within a very large system. The bulge appears bright and relatively smooth in optical and near-infrared images. This smoothness matters. Young stellar populations often create a patchy appearance because they gather in clusters and associations near gas-rich star-forming regions. An old bulge, instead, tends to look even and concentrated, with the light declining gradually away from the center. Near-infrared observations are especially helpful here because infrared light passes through dust more easily than visible light and traces the older, cooler stars that make up much of the stellar mass. In UGC 12591, the strong bulge remains prominent in such bands, reinforcing the conclusion that a large fraction of the galaxy's stars belong to an evolved central population. This makes the galaxy appear redder overall than a classic star-forming spiral with bright blue arms. The disk modifies this picture without overturning it. Along the plane of the galaxy, dust lanes interrupt the starlight. These lanes are not merely decorative marks. They show where cold interstellar material has settled into the rotating disk. Dust is mixed with gas, and together they define the regions where stars can form when conditions become dense and cool enough. In an inclined galaxy such as UGC 12591, these dusty structures can stand out sharply because they lie across bright background starlight from the bulge and inner disk. The effect is a visible contrast between luminous stellar emission and dark absorbing bands. Such dust features indicate that the galaxy is not completely stripped of the raw material for future star formation, even if its present activity remains weak. Color differences across the galaxy also suggest a transition from the redder inner regions to somewhat less red outer parts, though the system remains broadly mature in tone. This kind of gradient is common in large disk galaxies with prominent bulges. The center contains stars that are on average older and more metal-rich. In astronomy, metals are all elements heavier than hydrogen and helium. Repeated generations of stars enrich the gas with these heavier elements. So, older massive central regions often end up chemically richer than their outskirts. The outer disk can contain somewhat younger populations and lower average metal content, producing a modest shift in color. In UGC 12591, this transition appears consistent with a galaxy that builds a strong early central body and then maintains a quieter disk over long periods. Dust complicates these gradients in a useful way. Where the dust lane is strongest, visible colors may appear redder not because the stars are older, but because the dust dims the blue light more effectively. This is why multi-wavelength study is essential. A region that looks dark in visible images may become more transparent in the near-infrared, revealing the stars behind it. By comparing these views, astronomers can distinguish between stellar age effects and absorption by dust. For UGC 12591, such comparisons show that the dust is real and structurally significant, but not so overwhelming that it hides the overall identity of the galaxy. The dominant signal still comes from an old stellar system with a large bulge and a relatively subdued disk. The galaxy's broad spectral energy distribution, meaning the way its total light is distributed across wavelengths adds another layer to this interpretation. Ultraviolet emission is sensitive to recent star formation because short-lived massive stars shine strongly there. Mid-infrared and far-infrared emission can trace dust that absorbs starlight and re-radiates the energy at longer wavelengths. When all these bands are considered together, UGC 12591 appears notably quiet for a galaxy of its great stellar mass. The measured star formation rate is very low compared with what might be expected from a giant gas-bearing disk if it were vigorously active. This means the colours and dust must be read as signs of limited remaining activity within an otherwise largely quenched system. Quenched here means that star formation has fallen to a much lower level than in the galaxy's more active past. That low activity changes the meaning of the dust. In a strongly star-forming spiral, dust lanes often accompany brilliant blue associations, glowing nebulae, and widespread young clusters. In UGC 12591, the dust is present, but the surrounding stellar light does not suggest a galaxy in a major starburst phase. The dust instead belongs to a more restrained environment, perhaps the remnant of gas that has not been fully consumed or expelled, or material acquired and settled into the disk over long times. Observations indicate the galaxy has remained quiet for at least the recent span accessible to these star formation traces. This gives the visible structure a certain stillness. The disk holds its dust, but the galaxy does not blaze with fresh stellar birth. The colours also reinforce the hybrid nature of the system. A classic lenticular galaxy often appears smooth, red, and gas-poor, while a classic spiral tends to show more obvious blue arm structure and stronger signs of active star formation. UGC 12591 falls between these expectations. Its large bulge and red overall character lean toward the lenticular side. Its disk and dust lanes preserve key spiral-like ingredients. The result is a galaxy whose visible light records both inheritance and transition. It has the mature appearance of an early-type system, yet it has not fully lost the interstellar material associated with rotating disks. In this region of the inward path, the galaxy becomes legible through light alone. The bulge shines with the smooth red weight of old stars. The disk carries dust in settled lanes. The colours vary with radius, reflecting both stellar history and absorption. The full pattern points toward a very massive, evolved galaxy that still retains a structured interstellar medium but uses it sparingly. Nothing in this visible map requires unusual physics. It shows a calm but complex stellar system whose appearance is governed by age, composition, and dust. The eye now sees not just shape, but history written in colour and shadow across the galaxy's broad luminous body. At the outer edge of the visible disk, the galaxy's most striking property begins to dominate the story. UGC 12591 rotates with an extraordinary speed, measured from the motion of gas in the disk as it moves toward and away from the observer on opposite sides of the galaxy. In a rotating system, one side of the disk has a line-of-sight motion shifted toward shorter wavelengths, while the other side is shifted toward longer wavelengths. By comparing these shifts across the galaxy, astronomers reconstruct the rotation curve, the way orbital speed changes with distance from the centre. For UGC 12591, that curve rises to a value so high that the galaxy has long stood as one of the fastest rotating disk galaxies known. The reported speed is close to 500 kilometers per second at its peak, a value far above the characteristic rotation speed of the Milky Way and above the normal range for most large spirals. That number immediately carries physical meaning. Matter moving in orbit at such speed requires a very strong gravitational field to keep it bound. If the mass inside the orbit were too small, the gas and stars would not remain in long-term rotation. They should not be able to follow stable paths around the centre. The observed speed therefore acts as a direct sign of enormous enclosed mass. Even before the mass is carefully broken into stars, gas, and dark matter, the motion alone already shows that UGC 12591 is an exceptionally massive system. This result becomes even more impressive because it is measured in the disk, not in the random internal motions of an elliptical galaxy or in the deep central region around a black hole. Disk rotation is an ordered large-scale movement extending across tens of thousands of light-years. It reflects the structure of the whole galaxy, rather than a tiny inner core. The speed in UGC 12591 is therefore not a narrow local phenomenon. It is the motion of a giant rotating body. This is why the galaxy attracts such lasting attention. It is not merely massive, it is massive in a way that still preserves a broad disk supported by rotation. The outer rotation curve is the most revealing part because it tests how gravity behaves away from the dense centre. In many galaxies, speed rises through the inner parts where enclosed mass is growing rapidly, then reaches a broad plateau or changes only slowly farther out. If most of the mass were concentrated only in the bright inner region, the outer orbital speed would eventually decline in a more Keplerian way, meaning that motion would slow with increasing distance, much as planets do around a centrally dominant star. In large disk galaxies, observations often show something different. The speed stays high farther out than visible matter alone would suggest. UGC 12591 follows this broader galactic pattern, but at a far more extreme absolute speed. The galaxy does not appear to break gravity. It reveals how much mass must be present to sustain its extraordinary motion. At this stage, the speed record must be described with care. The exact maximum value can vary slightly between studies depending on inclination, resolution, adopted distance, and which tracer is used. Even so, the central conclusion remains stable. Observations consistently place the rotation speed of UGC 12591 at the very upper end of known disk galaxies, around the level that first made it famous in the classic measurements, and that later work continues to treat as exceptional. The scientific importance lies less in any single exact number than in the fact that the velocity is unmistakably enormous for a disk system that remains structurally coherent. Rotation speed by itself also does not say everything about the galaxy's condition. A high speed can belong to a compact object or a very extended one. The significance deepens when speed is combined with size. UGC 12591 is not a tiny dense remnant. It is a large disk galaxy. Gas at great distance from the centre still moves at a tremendous rate. This means the gravitational influence extends across a broad volume. The galaxy's rapid motion is not confined to a small bright nucleus. It is a property of the outer disk, where the enclosed mass must continue to grow or remain substantial with radius. The result is a rotating system that feels heavy at every large scale where its motion can be traced. One of the most useful ways to understand this is to compare ordered rotation with escape. A body orbiting too fast for the available mass would exceed the speed needed to remain bound. In that case, the outer gas would not stay in a settled disk over long times. Yet UGC 12591 does possess such a disk. The very existence of the ordered outer structure confirms that the galaxy's gravity is adequate to contain the motion. This is why the phrase that it defies gravity is only a poetic impression. In scientific terms, it does the opposite. It demonstrates gravity's reach by showing how much unseen and seen mass must together be present. The speed record also raises questions about rarity. Very massive galaxies certainly exist, but many of the most massive nearby systems are ellipticals, not giant rotating disks. Repeated mergers tend to randomize stellar orbits and reduce the dominance of coherent disk motion. UGC 12591 appears unusual because it combines enormous total mass with the persistence of a strong disk and measured rapid rotation. That combination is not impossible within current galaxy formation models, but it is uncommon enough to make the galaxy a valuable test case. It asks how a system can assemble such mass while still retaining large-scale ordered spin. This is also the first point where the outer to inner path touches the central mystery of the object without yet resolving it. The outer disk announces the problem in plain terms. The galaxy spins very fast, faster than ordinary visual intuition would expect from its luminous appearance alone. The disk remains intact, the motion is ordered, and the implied mass is immense. Nothing in this outer region yet specifies how much of that mass comes from stars, how much from gas, or how much from dark matter. Those pieces belong to later stages. Here, the outer rotation curve serves only as a measured fact and a boundary condition. Any successful account of UGC 12591 must explain why the outskirts move so rapidly while the galaxy preserves the form of a mature disk. Seen in this way, the rim of the galaxy becomes the place where the mystery first sharpens into quantifiable physics. The dark lanes and red bulge describe what the galaxy looks like, but the outer rotational speed declares what the galaxy must weigh. The two are related, yet not identical. Light alone does not predict the full force of the motion. The outer disk therefore becomes a silent instrument, marking the pull of the whole galaxy through the velocity of its gas. In these far reaches, UGC 12591 ceases to be simply a large handsome galaxy and becomes a dynamical extreme, a disk whose outskirts move with astonishing speed under the discipline of a very deep gravitational well. Once the unusual speed of the outer disk is recognized, the next task is to understand how that speed is actually measured. A galaxy does not carry labels on its edge stating how fast it turns. The value must be inferred from light, and the method depends on following the motion of material in the disk through its spectral lines. A spectral line is a narrow feature in light produced when atoms or molecules emit or absorb at specific wavelengths. If the source moves toward the observer, the line shifts slightly to shorter wavelengths. If it moves away, it shifts to longer wavelengths. This change is called the Doppler shift. In rotating galaxies, one side of the disk approaches while the other recedes, and the comparison between the two sides reveals the rotational motion. For UGC 12591, the classic measurements combine optical spectroscopy with radio observations of neutral hydrogen. Optical spectroscopy traces glowing gas in the disk through emission lines produced in ionized regions, while radio observations follow the 21 centimeter line of neutral hydrogen, the cold atomic gas that often extends farther outward than the bright stellar disk. These two approaches complement one another. Optical lines can offer good spatial detail in the inner and intermediate disk where the emission is detectable. Neutral hydrogen can reach farther into the outer parts, where starlight fades but gas still remains in orbit. Together they create a more complete picture of how rotational speed behaves across radius. The principle is straightforward, though the practice is careful. A spectrograph spreads light into its component wavelengths and records where known lines appear. If the spectrograph is placed along the major axis of a disk galaxy, meaning the longest apparent direction of the projected disk, then the strongest rotational signal appears there, on one side. The observed wavelengths are shifted in one direction. On the opposite side, they are shifted in the other. By measuring these changes at many points across the image, astronomers construct a velocity profile. In radio observations, the same idea applies, though the telescope measures the frequency of the neutral hydrogen line. Different parts of the rotating disk contribute emission at slightly different frequencies, and the pattern can be used to recover the velocity field. Inclination is central to this work. A galaxy seen face-on shows very little of its rotational motion along the line of sight, because most of the movement occurs across the sky rather than toward or away from the observer. A galaxy seen edge-on gives a much stronger line-of-sight signal. UGC 12591 is sufficiently inclined that its rotation projects well into the observed spectral shifts. Even so, the measured speed is not the full orbital speed until the inclination is accounted for. Astronomers must correct for the tilt of the disk. If the inclination is estimated incorrectly, the derived rotation speed will be too low or too high. This is one reason the exact quoted maximum velocity can vary somewhat between studies. The underlying result remains extreme, but careful work is needed to place the number accurately. Spatial resolution also matters. The central parts of a galaxy can show steep velocity changes over small distances, while the outer disk may require sensitive measurements of faint emission. If the instrument blurs together adjacent regions, the velocity gradient can be softened. This effect is known as beam smearing in radio work and has close analogues in optical observations. For a rapidly rotating galaxy, such blurring can obscure the true sharpness of inner changes and complicate the detailed shape of the rotation curve. Modern studies therefore compare different tracers and different instruments to reduce the risk of mistaking observational smoothing for real physical structure. Neutral hydrogen is especially valuable because it often extends beyond the bright optical disk. In many galaxies, the 21 centimeter line reveals gas at radii, where visible light is weak, and the stellar population alone no longer gives an easy dynamical guide. This is crucial for testing the mass distribution. If the rotation speed stays high in these outer gas-rich regions, then a large amount of mass must still be influencing the orbiting material there. For UGC 12591, the neutral hydrogen measurements help confirm that the galaxy's exceptional speed is not only an inner optical effect. The outer gaseous disk participates in the same extraordinary rotational regime. At the same time, each tracer has limits. Optical emission lines depend on ionized gas and active regions that may not fill the disk evenly. If star formation is weak, the emission can become patchy, reducing the number of positions where velocity is easy to measure. Neutral hydrogen observations can reach farther out, but the signal may be faint and the angular resolution coarser. The gas distribution itself may also show asymmetries, small warps, or local irregularities. For this reason, a rotation curve is never a direct photograph of pure circular motion. It is an interpretation of measured line shifts, corrected for geometry and assessed for possible deviations from perfect symmetry. What gives confidence in UGC 12591 is that multiple observations point in the same general direction. The disk is rotating extraordinarily fast. The line profiles also carry information beyond the simple maximum speed. Their width can reflect the spread of velocities within the beam, turbulence in the gas, and the overall dynamical breadth of the system. The full integrated hydrogen profile of a fast rotator is often very broad, signaling that gas across the whole disk spans a large range of line-of-sight speeds. In a giant inclined galaxy, this broad profile becomes a first indicator that the object is dynamically extreme, even before a detailed rotation curve is modelled. For UGC 12591, such broad line structure supports the image of a massive high-velocity disk. Uncertainty remains part of the scientific picture and must be stated plainly. Observations indicate very high rotational velocity, but the exact radial form of the curve and the precise decomposition into mass components depend on data quality, modelling assumptions, and the adopted geometry. It remains uncertain in detail how much the inner curve is shaped by the bulge, how the outer gas distribution may affect the recovered profile, and how far the rotation can be traced before the signal becomes too weak. These are normal uncertainties in galaxy dynamics. They do not erase the broad result. They define its precision. In this region of the inward journey, the galaxy is understood through method. Its speed is not an impression, but a measured property extracted from spectral shifts in light and radio emission. Optical lines trace glowing gas across the brighter disk. The 21 centimeter line of neutral hydrogen extends the reach into the outskirts. Inclination corrections, instrumental limits, and modelling choices shape the exact numbers, but the measurements converge on the same conclusion. UGC 12591 is an extraordinarily fast rotator. The evidence comes not from a single dramatic image, but from the patient reading of shifted wavelengths across a broad disk, where motion writes itself into light one line at a time. Once the rotation curve is measured, the next step is to ask what kind of mass distribution can produce it. The visible stars and gas provide part of the answer, but not all of it. In galaxies across the universe, the observed orbital speeds at large radii often remain higher than the luminous matter alone can support. This is one of the main lines of evidence for dark matter, a form of matter inferred from gravity but not directly seen in emitted light. Dark matter does not mean mysterious in the sense of arbitrary. It means matter whose presence is deduced from its gravitational effects. In UGC 12591, the need for such unseen mass becomes especially strong because the rotation speed is so large and remains significant far from the centre. A rotation curve can be translated into enclosed mass. The basic idea is simple. Faster circular motion at a given radius requires more mass inside that radius. In the bright inner galaxy, stars in the bulge and disk contribute strongly to the gravitational field. Gas also adds mass, though usually less than the stars in massive systems. Farther out, however, the light from stars declines while the rotation speed often does not fall as quickly as expected if visible matter were the whole story. The mismatch implies an additional extended mass component. In UGC 12591, the mismatch is not subtle. The galaxy is so fast and so large that a very substantial dark halo is required within standard gravitational modelling. A halo in this context is not a glowing ring. It is a broad three-dimensional distribution of matter surrounding the visible galaxy. Dark matter halos are thought to form first in cosmic history and then attract ordinary gas, which cools and settles into galaxies within them. The visible disk and bulge are therefore nested inside a much larger and more diffuse gravitational structure. In many galaxies, the halo becomes increasingly important with radius. Near the centre, stars may dominate the enclosed mass. Farther out, dark matter contributes a larger fraction. This general pattern appears to apply to UGC 12591 as well, though the galaxy's great stellar mass means that the luminous inner regions still matter strongly before the halo takes over. The remarkable speed of the outer disk suggests that the halo of UGC 12591 is not only present, but very massive. Studies that model the galaxy's baryonic matter, meaning its ordinary matter in stars and gas, find that the dark halo must provide much of the total gravitating mass needed to sustain the observed motion. This does not make the visible galaxy unimportant. The bulge and disk are themselves enormous, yet even a giant stellar system cannot by itself easily explain the full rotation profile. The galaxy's fame as a fast rotator therefore turns naturally into a study of halo scale. The disk becomes the tracer, and the dark halo becomes the gravitational framework that lets the disk move so quickly without flying apart. The halo also helps explain why the phrase that the galaxy defies gravity is scientifically misplaced. Gravity is not being resisted or contradicted. It is being revealed in full. The visible matter gives only part of the mass. The halo supplies the rest. When all significant mass components are included, the motion fits within the ordinary logic of orbital mechanics. The challenge is not that gravity fails, but that the mass distribution is much larger and more extended than the eye alone would infer from starlight. UGC 12591 therefore stands as a vivid example of how galactic dynamics can expose hidden matter with unusual clarity. Dark halo modelling is not perfectly unique. Different assumptions about the stellar mass-to-light ratio, the shape of the halo density profile, and the exact inclination of the disk can shift the balance between the visible and invisible components. A mass-to-light ratio is an estimate of how much stellar mass corresponds to a given amount of emitted light, and it depends on the ages and compositions of the stars. If the stars are assumed to be heavier per unit light, they can account for more of the inner gravity. If they are assumed to be lighter, the halo must shoulder more of the burden even near the centre. For UGC 12591, these details matter for precision, but not for the broad conclusion. The galaxy requires a massive extended halo under standard interpretations of the data. The halo's mass also connects the galaxy to the broader theory of galaxy formation. In current cosmology, the most massive disk galaxies live in large dark matter halos that gather gas over time. Whether that gas forms stars efficiently, remains hot in a surrounding reservoir, or is prevented from cooling by feedback processes depends on the halo mass and the galaxy's history. UGC 12591 appears to inhabit a halo massive enough to place it near the upper range, where disk survival becomes especially interesting. In many such large halos, the central galaxy may end up more spheroidal and less dominated by rotation after repeated mergers. The existence of a giant, rapidly rotating disk inside such a massive halo therefore makes this galaxy a valuable object for testing how baryons settle and how ordered structure can persist. The halo is also relevant to the galaxy's baryon fraction, the proportion of total mass made of ordinary matter. In the universe as a whole, ordinary matter is only a minority compared with dark matter. Individual galaxies do not always retain the same fraction expected from the cosmic average. Some lose gas through feedback, some fail to cool all the baryons associated with their halo, and some hide part of the baryonic matter in diffuse hot gas that is difficult to detect. UGC 12591 becomes important in this context because its enormous halo mass invites the question of how much ordinary matter it actually contains in stars, cold gas, and hot halo gas. The outer rotation curve does not answer that question fully, but it sets the scale on which it must be asked. This part of the inward journey therefore weighs the galaxy without seeing all of what is weighed. The disk's high speed demands a deep gravitational well. The stars and gas provide a luminous foundation, but the dominant large-scale structure must include an extensive dark halo. Observations indicate that this halo is very massive, consistent with the galaxy's extraordinary rotation and large size. It remains uncertain in detail exactly how the halo density changes with radius and how the visible matter shares the load in the inner regions. But the general requirement is clear. UGC 12591 is not simply a bright disk. It is a bright disk embedded in a dark matter structure of exceptional scale. In this region, the galaxy becomes more than an image and more than a velocity measurement. It becomes a gravitational system whose unseen mass shapes the fate of everything visible within it. The outer disk keeps tracing circular paths because a dark halo surrounds the galaxy with a pull far greater than starlight alone would suggest. The mystery deepens, but it does not drift into speculation. The explanation remains within the central framework of modern astronomy. A giant luminous disk turns at extraordinary speed because it lives inside an even larger invisible architecture of matter, one that gives the galaxy both its stability and its astonishing dynamical reach. The galaxy's great halo explains how such high speeds can be sustained at large radii, but the visible disk itself must also remain dynamically stable while rotating inside that deep gravitational field. Stability in a galactic disk does not mean perfect stillness. It means that the disk preserves its broad ordered form over long times rather than collapsing, fragmenting everywhere, or becoming so strongly disturbed that circular motion is lost. A rotating disk faces several competing tendencies. Gravity tries to draw matter together. Rotation helps support the disk against direct inward collapse. Random motions of stars and gas, along with pressure in the gas, resist small-scale compression. The structure that appears in UGC 12591 shows that these elements settle into a durable balance. Even though the rotational speed is extreme, the stellar disk is composed of stars on many individual orbits that, taken together, produce a flattened rotating system. Most of these stars move around the galactic center in the same general direction, but not all on perfectly circular paths and not all at exactly the same speed. Each star also has some random motion, including motion above and below the plane. This spread in velocities is known as velocity dispersion. In a thin, cold disk, dispersion is low, and the structure is more vulnerable to forming strong spirals, bars, or local instabilities. In a hotter disk, where random motions are larger, the system resists some of these patterns more effectively. Massive early-type disk galaxies often show this mixed character, strong rotation, but also enough internal random motion to keep the disk relatively smooth and to limit dramatic spiral structure. UGC 12591 fits this broad picture. Its disk remains clearly rotationally supported, meaning rotation provides much of the large-scale support against gravity. At the same time, the galaxy's prominent bulge and subdued arm structure suggest that the stellar system is not an extremely cold late-type spiral. The mass of the bulge contributes to the inner gravitational field and tends to stabilize the disk against the formation of large open spirals. The result is a massive disk that can rotate rapidly, while appearing comparatively ordered and restrained. This is an important point. Great rotational speed does not automatically imply a fragile disk. Under the right mass distribution, very fast motion can coexist with long-term structural coherence. Disk thickness enters the story here as well. A real galactic disk is not infinitely thin. Stars occupy a layer with measurable vertical extent, and that extent depends on the history of the system. Over billions of years, interactions with molecular clouds, spiral features, minor mergers, and internal gravitational scattering can increase the vertical motions of stars. Older populations therefore often inhabit a thicker distribution than young stars. In a galaxy as massive as UGC 12591, the stellar disk may be expected to include such a thickened component, especially because the system appears mature and bulge-dominated. A thicker disk can improve stability by reducing the strength of some self-gravitating disturbances. It also reflects the long, quiet accumulation of dynamical heating over cosmic time. The gas disk behaves somewhat differently from the stellar disk. Gas can cool through radiation, so it often settles into a thinner layer and responds more readily to compression. This makes gas the usual site of ongoing star formation and of visible structures such as dust lanes and nebula regions. But in UGC 12591, the current star formation rate appears low, which implies that the gas is not fragmenting into vigorous widespread stellar nurseries. Several factors can contribute to this. The gas surface density may be too low over much of the disk. The rapid rotation and strong shear may hinder collapse in some regions. The stabilizing influence of the galaxy's mass distribution may raise the threshold for large-scale fragmentation. Observations indicate a disk that holds gas and dust, yet does not convert them efficiently into new stars. This combination of massive ordered rotation and subdued star formation suggests a disk near the stable end of the spectrum for giant galaxies. It is not dead in the sense of containing no gas or dust at all, but it is calm. Such calm can be understood in terms of the balance between self-gravity and support. If the disk were too self-gravitating relative to its internal dispersion and rotational shear, it would develop strong clumps and sustained star-forming patterns. If it were too dynamically hot and poor in gas, it would appear even more like a classic lenticular with little interstellar structure. UGC 12591 occupies an intermediate state. It preserves a visible disk with dust and gas, yet much of that disk appears dynamically settled rather than actively restructuring itself. The extraordinary mass of the system also affects how disturbances travel through it. Spiral patterns, bars, and warps can arise through internal instabilities or external perturbations, but their strength depends on the disk-to-halo balance and on the concentration of mass toward the center. A very massive halo can reduce the tendency of the outer disk to develop large self-gravitating features. A strong bulge can further suppress bar formation, or at least alter how a bar would grow. The observational picture of UGC 12591, with its large bulge, limited spiral expression, and stable high-speed disk, is consistent with a galaxy in which these stabilizing influences are significant. There is, however, no claim that the disk is perfectly featureless or absolutely immune to disturbance. Real galaxies always contain asymmetries, local structures, and evolutionary traces. Small warps in outer gas layers, mild lopsidedness, or remnants of past minor accretion may still be present. It remains uncertain in detail how the fine structure of UGC 12591 compares with that of more typical giant disks, because such details can be hard to measure at its distance and inclination. What is clear is the large-scale outcome. The disk has not dissolved into disorder. It retains the kind of long-lived rotational architecture that allows the galaxy to be studied as a coherent dynamical system. This region of the story therefore turns the galaxy from a mere holder of a speed record into a durable mechanical structure. The disk does not simply move fast, it remains together while moving fast. The stars occupy a flattened rotating body with enough internal dispersion to resist severe instability. The gas settles into a thinner layer marked by dust. yet forms new stars only sparingly. The bulge and halo add stabilizing influence, and the total mass distribution allows extreme speed without widespread structural breakdown. UGC 12591 appears as a galaxy that has found a steady configuration at the very massive end of the disk population. The visible calm of the disk thus becomes part of the explanation, not merely a background detail. A galaxy that rotated so quickly without comparable structural support would likely reveal stronger signs of disruption or transient behavior. This one instead presents a mature rotating body whose form suggests endurance. The mass is enormous, the speed is extraordinary, and yet the disk remains legible as a stable large-scale system. In this inward step, the galaxy shows how gravity, rotation, and internal dispersion can cooperate to preserve order even under extreme dynamical conditions, allowing a giant disk to endure where simpler expectations might anticipate a more chaotic result. Beyond the bright stellar disk, the galaxy still carries a reservoir of cold atomic gas that can be traced through neutral hydrogen. This component matters because it extends the visible reach of the galaxy into regions where stars are sparse, and because it preserves a record of how the outer disk remains connected to the galaxy's deeper gravitational field. Neutral hydrogen is ordinary hydrogen in which the electron remains bound to the proton. It emits radio waves at a wavelength of 21 centimeters through a very rare quantum transition, and that line is one of the most important tools in extragalactic astronomy. It allows astronomers to map cold atomic gas across and beyond the optical body of a galaxy. In UGC 12591, this gas forms a key part of the outer story. The amount of neutral hydrogen in the galaxy is substantial, but not extreme compared with the most gas-rich late-type spirals. This distinction is important. UGC 12591 is not remarkable, because it contains an overwhelming ocean of cold gas. It is remarkable because it combines a large but fairly ordinary cold gas reservoir with an enormous stellar mass and an exceptionally massive total halo. The neutral hydrogen therefore appears as one component of a very large system rather than as the dominant substance of the disk. Observations indicate that the gas content is enough to trace rotation and to show that the galaxy retains a living interstellar medium, yet not enough to make the galaxy a highly active star-forming giant. The spatial extent of this gas is especially revealing. In many disk galaxies, neutral hydrogen stretches beyond the brightest visible stars. The reason is that atomic gas can remain at low density in outer regions, where star formation becomes inefficient. These outer layers are often faint in optical light but still dynamically important, because they orbit within the full gravitational potential of the galaxy. In UGC 12591, the hydrogen extends the measurable disk outward and provides the traces needed to confirm that high rotational speeds persist into those outer domains. It is through this cold gas that the galaxy's giant scale becomes more than a visual impression. The gas marks the continued presence of rotating matter in the outskirts, long after the starlight begins to fade. The structure of the neutral hydrogen disk also offers clues about the galaxy's recent history. A severely disturbed outer gas disk might point to a strong interaction, a major accretion event, or ram pressure stripping in a dense medium. A smoother disk suggests a quieter recent evolution. Observations do not indicate the kind of dramatic outer gas chaos expected from a major ongoing interaction. This supports the broader picture of UGC 12591 as a relatively isolated giant disk. Some asymmetry or subtle warp may still be present, as in many real galaxies, but the hydrogen distribution remains useful as an ordered tracer of the galaxy's large-scale rotation, rather than as evidence of catastrophic disruption. cold gas in outer disks also speaks to supply. A galaxy can form stars only from gas. A neutral hydrogen often acts as an intermediate reservoir from which denser molecular clouds may later develop. In that sense, the hydrogen in UGC 12591 represents potential as much as activity. It is a store of material that has not yet been fully transformed into stars. Yet the galaxy uses this store sparingly. The measured star formation rate is low for such a massive system, which means that the presence of hydrogen alone does not guarantee vigorous stellar birth. The gas must also cool, compress, and reach sufficient density in the right parts of the disk. In this galaxy, observations indicate that those conditions are met only modestly at present. The relationship between gas extent and halo mass is also important. An enormous dark matter halo can support a wide rotating gas disk by providing gravitational confinement far from the center. The hydrogen does not orbit in empty space. It remains bound because the galaxy's total mass reaches outward with it. In this way, the hydrogen disk becomes a visible outline of invisible gravity. Every measured point of cold gas in the outer galaxy confirms that the gravitational well extends across a vast region. The gas is thin and faint compared with the inner starlight, but dynamically it is one of the clearest witnesses to the size of the system. Gas content also helps place UGC 12591 among other very massive galaxies. Many giant early-type systems contain little cold gas and have largely ceased forming stars. Others, especially some large spirals, still hold abundant atomic and molecular material and continue active star formation. UGC 12591 appears intermediate. It retains a detectable and useful neutral hydrogen reservoir, yet not one that drives a strongly blue, actively growing disk. This fits the broader picture already suggested by its colors and morphology. The galaxy has not been fully stripped of disk material, but it also does not behave like a vigorous late-type spiral. Its outer hydrogen supports the image of a mature system that continues to carry cold matter without strongly rebuilding itself. There is still uncertainty in the detailed mass and distribution of this gas. The exact hydrogen mass depends on distance and flux calibration, while the inferred radial structure depends on sensitivity and angular resolution. At large distances, fine details can blur together, and the outermost low-density gas may be difficult to trace fully. It remains uncertain how far the hydrogen disk extends beyond the last reliable measurements, and whether faint diffuse gas lies still farther out. These uncertainties are normal and do not alter the main result. The galaxy clearly possesses a broad neutral hydrogen component that reaches into the outer disk and participates in its extraordinary rotation. This cold outer reservoir also carries a sense of temporal depth. Gas in these regions can remain in orbit for long periods, slowly evolving under the influence of the galaxy's potential. Mild accretion and internal dynamical processes. It need not be rapidly consumed. In UGC 12591, the neutral hydrogen seems to belong to this quiet long-duration state. It is not being violently torn away, nor is it being rapidly converted into stars across the whole disk. It remains as a calm outer companion to the stellar structure, broadening the galaxy's effective size and helping measure its motion at the edge of the visible system. In this region of the inward path, the galaxy's outer cold matter comes into focus as both substance and signal. The neutral hydrogen is not the largest mass component, but it is one of the most informative. It extends beyond the bright starlight, traces the rotation where luminous structure grows faint, and shows that the disk remains an ordered part of a vast gravitational system. It reveals a galaxy that is not empty at the rim, but still threaded with cold atomic gas moving in fast stable orbits. The outer disk is therefore not merely the end of the visible galaxy. It is a broad transitional zone where faint gas keeps the galaxy legible, far from the bright centre, carrying the record of mass, motion, and quiet persistence. Outside the cold atomic disk, the galaxy may also be surrounded by a much thinner and much hotter component of ordinary matter, a diffuse halo of gas heated to temperatures so high that it emits mainly in X-rays. This circumgalactic medium, meaning gas that fills the region around a galaxy but remains inside its larger gravitational domain, is difficult to detect because it is faint and spread over a broad volume. Yet for a system as massive as UGC 12591, such gas becomes especially important. A giant dark matter halo is expected to hold not only stars and cold gas, but also a reservoir of hot baryonic matter that has been heated as it falls inward and responds to the deep gravitational potential. The question is not simply whether hot gas should exist, it is how much of it is actually present and how far it extends. In a massive halo, incoming gas can be shock-heated. A shock in this context is a sudden compression that raises temperature and changes the state of the infalling material. Once heated to millions of degrees, the gas becomes too hot to emit much visible light. Instead, it glows weakly in X-rays. Telescopes designed for this part of the spectrum can search for broad, diffuse emission around galaxies and groups. Though the work is challenging, the signal is faint. Background emission from distant sources and foreground effects from the Milky Way must be accounted for carefully. Instrumental noise also matters. For UGC 12591, X-ray observations become a crucial test of whether a substantial hot halo can help explain the galaxy's baryonic budget. Observations indicate that hot gas is present, but not in the overwhelming quantity that might once have been expected for such an enormous system. This is one of the galaxy's most interesting modern results. The stellar mass is very large, and the total halo inferred from rotation is also very large. Yet the detected hot baryonic halo does not appear sufficient to bring the galaxy close to the full cosmic fraction of ordinary matter expected from its total mass. The X-ray emission therefore points to a circumgalactic medium that exists and matters, but remains comparatively modest relative to the scale of the halo. In this sense, the hot gas adds to the galaxy's ordinary matter inventory without completing it. The temperature of such gas is set by the depth of the gravitational well and by the history of infall and heating. In a very massive system, one expects a hot atmosphere in approximate hydrostatic balance, meaning that the outward pressure of the gas partly balances the inward pull of gravity. This need not imply perfect equilibrium at every radius, but it provides a useful framework for interpreting the X-ray brightness profile. The gas density generally decreases with distance from the center, causing the emission to fade outward. Because X-ray brightness depends strongly on density, the outer regions can become extremely difficult to observe even if gas is present there. This is important for UGC 12591. A faint detection does not necessarily mean no gas exists beyond the measured region. It means only that the observations become progressively less sensitive to very diffuse outer material. This uncertainty shapes the interpretation. Observations indicate a hot halo component, but it remains uncertain exactly how much diffuse gas lies at still larger radii below current detection thresholds. Astronomers can model how much undetected gas might exist by extrapolating the observed density profile. Yet such extrapolations depend on assumptions about how the profile continues outward. A shallow profile could hide substantial mass at large distances. A steeper profile would contain much less. For UGC 12591, the available X-ray data suggest that even with reasonable extrapolation, the total hot gas mass remains insufficient to erase the broader baryon deficit implied by the halo mass. This does not close the question completely, but it narrows the plausible range. The hot halo also matters because it affects the future of the disk. Gas at these temperatures does not readily collapse into stars. It must first cool, losing energy before it can sink inward and contribute to colder phases. In very massive halos, the cooling time of diffuse hot gas can become long, often longer than the timescales on which active star formation would require replenishment. This provides one possible reason why a giant galaxy can retain a large halo and yet form stars only weakly. The gas associated with the halo may exist mostly in a state too hot and too diffuse to feed the disk efficiently. In UGC 12591, the low present-day star formation rate fits naturally with this picture of a system whose surrounding ordinary matter is not rapidly condensing into new stellar growth. Hot gas is also relevant to feedback, the process by which energy from stars, supernovae, or an active nucleus influences the surrounding medium. Feedback can heat gas, drive outflows, and reduce the efficiency with which baryons cool and settle into the galaxy. In a system as massive as UGC 12591, supernova heating alone is unlikely to dominate the entire circumgalactic environment, but over long periods it can still contribute. A central black hole, if active at some stage, may also inject energy into surrounding gas. It remains uncertain how strongly such feedback has shaped the present halo of UGC 12591, but the modest hot gas detection is at least consistent with a history in which cooling has not been completely free to build a much denser X-ray atmosphere in the inner circumgalactic region. The contrast between the hot halo and the cold atomic disk is one of the galaxy's quietest and most revealing features. The cold gas lies in a flattened rotating layer, observable through the 21-centimeter line and associated with dust and limited star formation. The hot gas is diffuse, roughly spherical or broadly extended in 3 dimensions, and visible only through faint X-rays. These two states of matter belong to the same galaxy, but occupy very different thermal and dynamical regimes. One is cool enough to remain in the disk. The other is heated to the point where it lingers in the halo. UGC 12591 contains evidence for both. Yet neither phase appears abundant enough by itself to dominate the total mass budget in comparison with the dark halo and the huge stellar population. In this region, the galaxy's outer ordinary matter becomes thinner, hotter, and harder to see. The hot circumgalactic gas does not announce itself the way the stellar bulge or the fast outer disk does. It appears only through careful X-ray work and careful modelling. Still, it adds an essential piece to the story. UGC 12591 is not merely a disk of stars and cold gas inside a dark halo. It is also surrounded by a faint hot atmosphere of ordinary matter, one that confirms the scale of the halo, but also reveals its incompleteness as a baryon container. The detected X-ray glow is real, informative, and limited. It shows that the galaxy holds hot gas, but not enough to solve by itself the deeper accounting problem of where all the expected ordinary matter has gone. With the stars, cold gas, hot gas, and dark halo now in view, the galaxy can be examined as an accounting problem. This is the level where astronomers ask whether the amount of ordinary matter detected in and around UGC 12591 matches what would be expected from a halo of its inferred total mass. Ordinary matter, or baryonic matter, includes stars, stellar remnants, cold gas, warm gas, and hot gas. Dark matter is counted separately. Cosmology provides a reference value for the average cosmic share of ordinary matter relative to total matter. If a galaxy halo were to retain that full share, then a certain baryon mass would be expected once the halo mass is known. In many real galaxies, however, the observed baryonic total falls short. UGC 12591 is one of the clearest and most striking examples of this shortfall among very massive disk galaxies. The stars account for a very large baryonic component. The galaxy's stellar mass is immense, and much of it resides in the bulge and the massive disk that dominates the visible light. Cold atomic gas adds another contribution, though smaller than the stars by a wide margin. Hot circumgalactic gas contributes more, but observations indicate that it is still not nearly enough to fill the gap between detected baryons and the amount implied by the galaxy's large halo. When these known baryonic components are added together, the total remains well below the cosmic baryon fraction. In plain terms, the galaxy appears to be missing a substantial amount of ordinary matter relative to what its total mass suggests it should have. This missing baryon problem does not mean that matter has vanished in a literal sense. It means that the detected baryons associated with the galaxy and its inner halo fall short of the expected share. Several possibilities can contribute to such a deficit. Some baryons may never cool efficiently into the galaxy and may remain dispersed at very low density in the outer halo, too faint for present observations to detect. Some may have been heated and pushed outward by feedback processes over long spans of time. Some may lie beyond the radii that have been measured directly. The challenge in UGC 12591 is that even after accounting for these possibilities in reasonable models, the observed deficit remains substantial. The galaxy's importance here lies in its mass scale. Lower mass galaxies often lose baryons more easily because their shallower gravitational wells make it easier for energetic outflows to escape. A giant halo like that of UGC 12591 should, in principle, be better able to retain ordinary matter. Yet the baryon fraction still appears lower than the cosmic average. This result suggests that the missing baryon problem is not limited to small fragile systems. It can persist even in enormous galaxies with very deep gravitational potentials. That makes UGC 12591 a particularly useful laboratory for testing how baryons are acquired, heated, stored, and hidden across cosmic time. The accounting itself depends on measurement choices and model assumptions, and these must be stated carefully. The halo mass inferred from the rotation curve carries uncertainty. The stellar mass depends on the adopted mass-to-light ratio and the assumed stellar population model. The cold gas mass depends on flux measurements and distance. The hot gas mass depends on X-ray brightness, temperature estimates, and the extrapolation of a density profile to larger radii. For these reasons, no single baryon fraction should be treated as exact to many decimal places. Even so, the broad conclusion is robust. Across reasonable assumptions, UGC 12591 appears baryon poor relative to the full cosmic share expected for its halo. This conclusion has wider implications for galaxy formation theory. It suggests that the relationship between halo mass and retained baryonic matter is not a simple one in which bigger halos automatically keep proportionally more of everything they are allotted by cosmology. Instead, the final baryon content depends on the competition between accretion, heating, cooling, star formation, and feedback. In a system this massive, much of the gas may spend long periods in hot diffuse form, unable to cool efficiently into the disk. Some may remain so extended and so thin that it escapes easy detection. The observed low present-day star formation rate is consistent with this picture. The galaxy has built a huge stellar system in the past, yet does not now appear to be efficiently turning surrounding baryons into new stars. The deficit also shapes how the galaxy is compared with other massive systems. Rich galaxy clusters often hold large amounts of hot X-ray emitting gas and come closer to the cosmic baryon fraction when their full volume is considered. Individual galaxies, even very massive ones, often do not. UGC 12591 lies in an interesting middle ground. Its halo is enormous for a single disk galaxy, but it does not seem to contain the kind of dense, hot intracluster medium that would close the baryon gap in the way clusters can. This distinction helps explain why the galaxy can be both very massive and still baryon deficient. It is not a cluster-scale environment. It is a giant galaxy-scale halo with incomplete visible baryon retention. There is also a conceptual shift in this part of the story. Earlier sections ask what the galaxy looks like and how fast it rotates. Here the galaxy is treated as a census. Light, radio emission, and X-rays become methods of counting. Each observed component adds another entry in the ledger. The stars carry much of the known ordinary mass. The atomic gas adds a smaller line. The hot halo adds another. Yet the sum still does not meet the expected total. The quiet force of this result is one reason the galaxy remains so interesting. Its extraordinary rotation implies a very large halo, and that halo in turn creates a strong expectation about baryons that the observations do not fully satisfy. It remains uncertain where all of the missing baryons associated with UGC 12591 ultimately reside. Observations indicate that some may be hidden in very diffuse outer gas beyond current X-ray sensitivity, but it remains uncertain whether such gas is abundant enough to close the gap. It is also uncertain how much baryonic matter may have been displaced by long-term feedback, and how much simply failed to condense into the galaxy's observable regions. These uncertainties are active areas of study, but they do not weaken the main finding. They define its frontier. The galaxy has become a clear case where ordinary matter is not seen in the quantity. Cosmological expectation might suggest. In this region of the inward path, UGC 12591 becomes an exercise in missing weight, not of total gravity but of visible and detectable ordinary substance. The dark halo seems large enough to demand more baryons than are found in stars, cold gas, and observed hot gas combined. This gives the galaxy a second kind of mystery beyond its rapid rotation. It is not only a giant disk that moves unusually fast, it is also a giant disk whose ordinary matter appears incomplete. The ledger does not balance, and that imbalance stands as one of the galaxy's most revealing scientific features, measured not in spectacle, but in absence. From the broad accounting of matter, attention now returns to the living processes still at work inside the disk itself. The key question in this region is not how much total mass the galaxy possesses, but how actively that mass is being transformed into new stars. Star formation is the process by which dense cold gas collapses under gravity into compact objects hot enough to ignite nuclear fusion, in galaxies with rich supplies of cool, dense gas. This process can proceed across spiral arms and dust lanes, lighting the disk with short-lived blue stars and glowing nebulae. In UGC 12591, however, observations indicate a much quieter state. The galaxy still contains dust and cold atomic gas, but its present rate of star formation is low for a system of such enormous size. This low activity gives the disk a distinctive character. A massive disk galaxy might be expected, at first glance, to host widespread stellar birth simply because it has so much material and such a large physical extent. Yet galaxies do not form stars according to size alone. The gas must cool enough, settle into dense clouds, and overcome the stabilizing influences of rotation, turbulence, magnetic fields, and the surrounding gravitational environment. In UGC 12591, those conditions appear to be met only sparingly. The galaxy remains capable of forming stars, but it does so with restraint. The result is a system whose visible disk still bears the materials of star formation, without displaying the vigorous renewal seen in more actively growing spirals. The evidence for this calm state comes from several parts of the spectrum. Ultraviolet light traces young, massive stars that live only a short time. So weak ultraviolet emission indicates limited recent star formation. Infrared emission from dust can also help, because dust absorbs starlight and re-radiates it at longer wavelengths. In strongly star-forming galaxies, warm dust often glows brightly as it is heated by young stellar populations. In UGC 12591, the combined picture from these indicators points toward modest ongoing activity rather than a strong burst. The dust is present, but it is not being intensely heated across the disk by widespread newborn stars. This matters because the galaxy's outward appearance might otherwise mislead. The dust lane suggests a disk that still contains interstellar material, and the great size of the galaxy suggests a wide arena for star-forming clouds. Yet the star formation efficiency appears low. Efficiency in this context means how effectively the available gas is converted into stars over time. A galaxy may possess gas and still form stars slowly if much of that gas remains too diffuse, too warm, or too strongly stabilized against collapse. In such a case, the disk becomes a place of stored potential rather than rapid creation. UGC 12591 seems to occupy that state. It keeps some of the ingredients for star formation but uses them at a subdued pace. The structure of the galaxy helps explain this. A large bulge contributes strong central gravity and can help stabilize parts of the disk against the growth of large self-gravitating disturbances. The rapid rotation of the disk also introduces shear, meaning that neighboring rings of material move at different speeds. Shear can stretch gas clouds and make it harder for them to collapse coherently on large scales. In a more gas-rich late-type spiral, these stabilizing effects may be offset by abundant cold dense gas and stronger spiral structure. In UGC 12591, the balance appears different. The stabilizing influences are substantial, while the gas supply that remains in the star-forming phase seems relatively limited. The star formation that does occur is likely concentrated in the disk rather than in the bulge, because star formation depends on cold gas and dust that settle into the galactic plane. Even so, the disk does not resemble a classic blue star-forming system with brilliant knots and strong open arms. Its star-forming regions, where present, are quieter and less dominant in the galaxy's overall light. This is consistent with its broad color pattern, which is weighted toward older stellar populations. The galaxy's great mass is therefore not being built rapidly in the present era. Most of its stars must have formed earlier, during periods when the gas supply and internal conditions allowed much more efficient stellar production than is observed now. That historical contrast is important. UGC 12591 is not a small dormant relic. It is a giant galaxy that has clearly succeeded in building an immense stellar body. The current low star formation rate does not mean the galaxy was always quiet. It means that the present epoch is one of mature, reduced activity. At some earlier time, The galaxy must have formed stars at a much higher rate in order to assemble its huge bulge and disk. The visible evidence now suggests that this era of stronger growth lies mostly in the past. The galaxy retains the memory of that growth in its stellar mass, while its present light reveals a more settled and restrained phase. This quietness also links naturally to the hot halo and baryon deficit described earlier. If much of the surrounding gas remains hot and diffuse, then it cannot easily replenish the cold, dense phase needed for rapid disk star formation. If the available cold gas reservoir is moderate rather than abundant, the disk may continue to form stars slowly for a long time without entering a major burst. In that sense, the low star formation rate is not an isolated fact. It is part of the galaxy's wider state. UGC 12591 appears to be a very massive system that has already done most of its stellar building and now evolves in a quieter mode, held steady by a large halo, a mature bulge, and a relatively calm disk. Even the dust takes on a different meaning in this context. In an active spiral, dust can signal crowded stellar nurseries and constant renewal. Here it signals continuity rather than frenzy. The dust lane shows that the disk has not been stripped clean, and that interstellar matter still survives in organized form. But the subdued ultraviolet and infrared signatures indicate that this matter is not being rapidly transformed. The galaxy is neither barren nor prolific. It is conservative. It forms stars at a rate that is real but modest, especially when judged against the enormous scale of its mass and rotation. In this region of the inward path, the galaxy is understood as a quiet workshop rather than a blazing factory. Its disk still carries dust and gas, and those materials still support some ongoing stellar birth. Yet the overall level of activity remains low. Observations indicate a system that has matured, one in which most of the visible mass comes from older stars and most of the dramatic building lies behind it. UGC 12591 therefore deepens its mystery in a gentle way. It is not only very massive and very fast, it is also unexpectedly calm in the one process that most visibly renews galactic disks. The giant structure turns on, but it no longer grows with urgency. It preserves its vast form while adding new light only slowly, almost reluctantly, within the broad, settled lanes of its disk. After the outer disk, the gas reservoirs, and the quiet pace of recent star formation, the galaxy now narrows inward toward its dominant central stellar structure. The bulge of UGC 12591 is not a minor swelling at the center of the disk. It is a major component of the galaxy's visible mass, and one of the clearest signs that this system belongs to the early type end of the disk galaxy family. A bulge is a central concentration of stars that rises above the thin plane of the disk and shines with a smoother, rounder profile than the surrounding flattened structure. In a massive galaxy such as this one, the bulge is both a record of the past and an active part of the present gravitational field. The light from the bulge is redder and more uniform than the light in the disk. This visual difference reflects a stellar population dominated by older stars, stars that have already passed the brief bright phases associated with youth and now contribute a more stable glow. The smoothness of the bulge suggests that its stars are dynamically mixed, compared with the more ordered pattern of the disk. While the disk owes its appearance to stars moving mainly in the same rotational plane, the bulge contains stars on a broader range of orbits, including orbits that carry them well above and below the plane. This gives the bulge a fuller three-dimensional form and makes it appear more spheroidal in projection. In galactic structure, the bulge is important because it changes how gravity is distributed in the inner regions. A concentrated central mass causes the inner rotation curve to rise steeply, It also deepens the potential well through which stars and gas must move. In UGC 12591, the very presence of such a large bulge means that the transition from disk-dominated gravity to centrally concentrated gravity occurs well before the galaxy reaches its smallest scales. The bulge therefore acts as the gateway to the central interior. It gathers stellar mass inward and shapes the motions of the surrounding disk, even before any unresolved nuclear source comes into consideration. The formation history of such a bulge is written only indirectly in the present-day observations, but the broad picture is reasonably clear. A large bulge usually implies that much of the central stellar mass forms early or is assembled efficiently over time through internal and external processes. Rapid early gas inflow can create a dense central stellar system. Mergers, especially in the earlier universe, can also contribute stars and drive gas inward. Internal secular evolution, meaning gradual structural change caused by the galaxy's own long-term dynamics, can further reshape the inner disk and build central concentration. For UGC 12591, observations indicate an evolved and massive bulge, but they do not by themselves assign one single pathway with certainty. The current state is clear even if the exact sequence of past events remains partly uncertain. The bulge also helps explain the galaxy's restrained spiral structure and low present-day star formation. A prominent central concentration tends to stabilize the inner disk against some forms of gravitational instability. It can suppress the development of strong open spiral arms and alter how gas responds to perturbations. In this way, the bulge is not simply an old inert mass of stars, it remains an active structural influence on the surrounding galaxy. UGC 12591 appears more settled, more compact in its center, and more conservative in its disk behavior because the bulge is so substantial. The stellar populations in the bulge are expected to be both older and more metal-rich than those in the outer disk. Metal-rich in astronomy means enriched in elements heavier than hydrogen and helium by previous generations of stars. Repeated cycles of star formation and stellar death gradually increase this enrichment, especially in dense central environments where gas is processed efficiently. The red color and strong near-infrared light of the bulge are consistent with such a mature, enriched population. This matters because it tells a story of early effectiveness. The center of the galaxy has not merely accumulated stars. It has done so through a history long enough and intense enough to enrich its material and leave behind a dominant old stellar body. At the same time, the bulge must not be confused with the nucleus itself. The bulge extends over a large central volume compared with the truly innermost region. It is resolved in images as a broad, bright central structure. The nucleus, by contrast, belongs to the much smaller scales that will only come into view at the next inward step. Here the focus remains on the bulge as the last major visible stellar region before the unresolved center. It is the inner heart of the galaxy in the sense of mass and light, but not yet the final core. The shape of the bulge may also preserve clues about whether it is closer to a classical bulge or a pseudo-bulge. A classical bulge is more spheroidal and typically linked with violent early assembly or mergers, while a pseudo-bulge is more disk-like and often grows through slower internal rearrangement. In practice, real galaxies can show mixed properties. For UGC 12591, the prominence, red color, and early type character favor a substantial classical bulge component, though detailed decomposition can depend on imaging depth and modeling choices. What is not in doubt is the scale of its central stellar concentration. The galaxy's visible mass is not spread thinly across the disk alone. It is gathered powerfully toward the center. This concentrated stellar body changes the emotional geometry of the galaxy. The outer disk is broad, thin, and fast. The bulge is dense, rounded, and steady. The contrast gives UGC 12591 much of its character. It is a giant disk galaxy, yet its center carries the visual weight of a much more condensed system. The eye is drawn inward from the long dusty plane to a bright central mass that seems to hold the galaxy together. That impression is not merely visual. It reflects a real concentration of stars and gravity. In this region of the inward path, the galaxy is understood through the dominance of its bulge. The broad disk still exists around it, but the center now rules the light. Older stars fill a thickened spheroidal structure above the plane. The gravitational field grows steeper and more concentrated. The stellar populations become redder, richer in heavy elements, and more dynamically mixed. UGC 12591 appears here as a galaxy that has built not only a fast outer disk, but also a powerful interstellar mass, a mature core of old stars that anchors the visible system. This bulge is the final large resolved structure before the story reaches the smallest scales, where the bright central body gives way to the much harder question of the true nucleus hidden within it. At the smallest accessible scale, the broad bulge gives way to the nucleus, the compact central region where the galaxy's light becomes most concentrated, and where the deepest part of the gravitational potential is expected to reside. In many galaxies, this innermost zone may host a supermassive black hole, a central object whose mass can range from millions to billions of times the mass of the Sun. Such black holes do not shine by themselves. They become visible only when gas falls inward, heats up, and radiates energy before crossing the event horizon. If that process is strong, the nucleus can appear as an active galactic nucleus, a compact source whose emission stands out from the surrounding stars. In UGC 12591, the nucleus is not known as a spectacular active center. The evidence points instead to a much quieter inner state. This calm does not imply emptiness. The galaxy's enormous bulge makes it very likely that a supermassive black hole exists at its center. Because such black holes are common in massive bulge-dominated galaxies, observational studies of many galaxies show broad correlations between bulge properties and central black hole mass. These correlations do not predict an exact value for any one galaxy, but they support the expectation that a substantial black hole should inhabit the core of UGC 12591. The important caution is that expectation is not the same as a precise direct measurement. At the distance of this galaxy, resolving the sphere of influence of a central black hole, meaning the region where its gravity clearly dominates over the surrounding stars, is difficult. The nucleus therefore remains more constrained by inference than by fine direct mapping. The inner kinematics, or motions, are also harder to recover than those of the outer disk. In the outer galaxy, rotating gas and neutral hydrogen provide extended traces. In the central region, the light is crowded, the velocity gradients are steep, and the bright bulge can outshine more delicate features. Gas in the nucleus, if present, may not move in simple circular patterns. Stellar motions can provide clues, but they require high-resolution spectroscopy and careful modelling to separate the contributions of the bulge, the inner disk, and any compact central mass. For UGC 12591, this means the nucleus is scientifically less exposed than the outer rotation curve. The galaxy is famous because its outer disk is easy to identify as extraordinary. Its innermost core is subtler and less directly accessible. This imbalance is revealing in itself. Many galaxies draw attention through luminous nuclei, jets, or intense central activity. UGC 12591 does not owe its identity to such features. Its mystery is carried instead by the broad mechanics of the whole system. The nucleus remains comparatively quiet, and that quietness fits the broader state of the galaxy. Star formation is subdued. The hot halo exists but is not overwhelmingly dense. The disk rotates rapidly yet remains stable. The center, too, appears to be in a low-activity state rather than a violently accreting one. If a supermassive black hole is present, it does not currently dominate the galaxy's appearance through radiant outburst. There may still be weak nuclear activity below the level of a bright quasar or powerful active galaxy. Many massive galaxies contain black holes that accrete at low rates, producing only faint signatures in optical radio or X-ray observations. Such activity can be difficult to isolate from the surrounding bulge light and from other compact emission processes. Observations indicate no need to invoke a strongly active nucleus to explain the present properties of UGC 12591. It remains uncertain whether the central black hole is accreting at a very low level. But if so, that activity does not appear to define the galaxy in the way the giant disk and huge mass do. The nucleus also represents the endpoint of inward transport. Over cosmic time, gas may lose angular momentum and drift toward the center through bars, interactions, or internal torques. Some of that material can form stars in dense central regions. Some may feed the black hole. In a galaxy such as UGC 12591, much of this decisive central growth seems to belong mainly to the past. The bulge is already enormous. The current star formation rate is low. The nucleus is not powerfully active. These signs together suggest that the central engine of assembly has largely quieted, even if slow inward drift and weak accretion may still continue. The core of the galaxy is therefore not a scene of dramatic transformation at present. It is a region of concentrated mass and restrained activity. The uncertainty at the center should be stated honestly. Observations indicate a massive bulge and make a central supermassive black hole highly probable. But it remains uncertain what the black hole mass is to any high precision without stronger direct dynamical constraints. It also remains uncertain exactly how the innermost gas and stars are arranged on scales too fine for the present broad picture to resolve. These uncertainties are not failures. They mark the natural limit reached when the story moves from the galaxy's huge visible body into its smallest hidden region. The farther inward the path goes, the less the eye can see directly, and the more careful interpretation must replace direct image-based certainty. Even so, the nucleus completes the logic of the galaxy. The outer cosmic web places UGC 12591 in the large-scale architecture of matter. The local environment shows it living with relative independence. The disk reveals extraordinary rotational speed. The halo supplies the hidden mass that makes that speed possible. The gas and dust show restrained ongoing life. The bulge concentrates the stellar body inward. At the center, the nucleus gathers all of these trends into their smallest volume. It is the quiet endpoint of a galaxy built on scale, weight, and control. Nothing here suggests that gravity is broken. Everything suggests that gravity has worked for a very long time, drawing matter inward, sorting it into disk, bulge, halo, and finally nucleus. In this final region, UGC 12591 becomes almost still. The giant outer motion remains real, but it is no longer the visible theme. The center is compact, luminous, and difficult to fully resolve. It likely contains a supermassive black hole, yet it does not flare with the violence seen in some galactic cores. The innermost galaxy appears mature, massive, and calm. The mystery of UGC 12591 therefore ends not in an explosion of central drama, but in quiet concentration. At the smallest scale, the galaxy holds a dense, unresolved core inside an immense rotating structure, a final compact heart concealed within the great body whose speed first draws attention from far away. The galaxy now rests as a complete structure, from the filaments of the cosmic web down to the quiet center hidden inside its bulge. UGC 12591 does not overturn the laws of the universe. It reveals them with unusual clarity. A vast halo of dark matter surrounds a giant luminous disk. Stars gather densely in the bulge. Dust and cold gas remain in the plane. A thinner hot atmosphere lingers beyond. The outer disk turns with exceptional speed, and that speed quietly measures the depth of the gravitational well in which the whole system lives. Observations indicate a galaxy of enormous mass, unusual rotation, low present-day star formation, and an incomplete visible baryon inventory. Some ordinary matter shines as stars, some drifts as cold atomic gas, some glows faintly in hot X-rays. Yet a large share remains uncertain in location, likely spread too thinly or too far out to be easily seen. The galaxy's great lesson lies in that balance between what is visible and what is inferred. Light shows the surface of the system. Motion reveals its hidden weight. Its mystery is therefore gentle rather than violent. The dust lanes, the red bulge, the broad hydrogen disk, and the faint hot halo all belong to a single calm order. Nothing rushes, nothing breaks. The giant structure simply turns, held together by gravity across distances so large that the eye can only gather them slowly. In that slow turning, the galaxy keeps its deepest truths in motion rather than in brightness. The stars tell part of the story. The orbiting gas tells the rest. UGC 12591 remains a quiet reminder that the universe often hides most of its substance behind ordinary light, leaving motion to speak where sight cannot. In the dark beyond the bright central bulge, the outer disk continues its vast measured circuit, and the great galaxy endures in silence.